Consider the parametric curve. 2 log t squared plus 1 plus 5, comma, 6 arctangent t plus t minus 4. Now, when we write that, you really should think of it as the first slot, this is your x, and the second slot, this is your y. Sometimes we'll write x of t equals this, y of t equals that. Sometimes we'll put into coordinate pairs. But okay, so we have this parametric curve, and there's a question. For which of the following values of t is the tangent line at the point on the curve corresponding to t? So in other words, for every t, there is a point on the curve, and most points have a tangent line. So at which values of t are we parallel to y equals 2x minus 9? And we have 5 options. 1, 2, 3, 4, or 5. Well, what's the answer? Has anybody worked on this yet? 1? Is that your guess, or is that the answer? It is the answer. 1 is right. Nice. All right. So, what does it mean for things to be parallel? Same slope. All right, so now we say, great. We need to make sure our slope is 2. Slope is derivative. So we say, okay, derivative equals 2. How do you find derivative for parametric curves? Y prime of t over x prime of t. So we get to the conclusion, we need y prime of t to be 2x prime of t. So we take y prime equals 2x prime. Well, fractions are dangerous. And I try to get rid of them as soon as I can. Can't always do it, but a lot of times we can. And so we can get rid of fractions by multiplying through both sides by this quantity of t squared plus 1. That gets rid of our fractions, so we reduce down to a polynomial equation, 6 plus t squared plus 1, which is 6 t squared plus 1 equals 2 times 2 times 2 t, or 8t. And that's quadratic. We have ways. And so it turns out that there are 2 values for t that work. 1 or 7. We were just asked to identify which of the following. And so only 1 is on that list. So there we go. All right. Any questions on this one? Okay. Well, thought for the day from Zig Ziglar. You don't have to be great to start, but you have to start to be great. You know, there's this sort of notion of like, I can't start studying yet. I'm not ready. Or I can't start preparing. I need to wait for something to happen. Only when I'm sufficiently ready can I begin. But with that mindset, you delay and delay and delay, and you never start. It's okay that you're not perfect when you start. And that's kind of the point. You prepare and you get better. So don't push off getting ready for, say, an exam. The best time to start getting ready for the exam was back at the beginning of the semester. The second best time is today. So start getting ready. The more you space it out, the better it'll be. Less stress we'll have. And I'm a big fan of not being stressed out. All right, well, what are we doing today? Last time we talked about length for parametric curves, but we really didn't get enough time to talk about application, so we're going to talk about that. And then we're going to get into polar coordinates. And here, what are polar coordinates? Well, they're a way of describing points in the plane. And we're so used to Cartesian coordinates that we say, well, that just seems to be the way, right? Isn't that the only way? But there's other ways. And it all comes down to what's convenient and what makes things simple. So we'll talk about what polar coordinates are, and we'll talk about the different coordinate systems. And in particular, we have our x's and y's. We're going to introduce polar, which has r's and thetas, and we're going to have these formulas. X equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. And if you look on your formula sheet, you'll see that that shows up on your formula sheet. So, good. It's nice to be back on the formula sheet again. So let's jump in to our applications. And there's some comments that says, look, any application which we did for y equals f of x, we can really go and do it for parametric curves. Now, there's a couple of applications, and I kind of grouped them into two camps. There's applications which relied on length, and those are going to be simpler to adapt. Because for length, it's a measurement. There's no orientation. So orientation does not come into play. And you might say, what's orientation? We'll get into that. But essentially, you should think about orientation is, how do you move? Because when you think about parametric curves, you're really describing your location at a given time t. So you can think about it as you're moving along the curve, and the curve is tracing where you've been. But how do you move on that curve? Left to right or right to left? Now you might say, we haven't ever worried about orientation before. Why do you bring it up now? Well, we have worried about orientation. It's just always been the same way. The x-axis has an orientation built into it. And now it's like, oh, we have to think about what's going on. So with length, there's no worry. It's about orientation. Sometimes it's not length. And for that, we do have to worry about orientation. And the good news is, you might say, oh, that makes things worse. But orientation can also make things better. And there's lovely things that can happen. And we'll see that in some examples. All right, so let's do an example with surface area. So, what's our generic formula? 2 pi times radius times length. And that's just the formula straight from the equation sheet. And it's written this way to be flexible, so that we can adapt it to any situation we might encounter. So we say, all right, if we're in parametric, we know how to handle length. That's what we did last time. Length is the square root x prime squared plus y prime squared dt. So, an example. Find the surface area when this curve, log of secant t plus tangent t minus sine t comma cosine t, t going from 0 to pi over 4, is spun around the x-axis. And we're like, cool. What does this look like, you might wonder? And, good question. Well, I don't know. Let's say it looks like that. We just draw something, just a sketch to sort of get us going. Now, it's probably wrong, but that's okay. It's definitely wrong, and that's okay. All right. But there's a curve. So let's say this is our curve, and we're spinning around the x-axis. So you say, all right, good. And how does length work? Well, how does surface area work? We're thinking about cutting things into little pieces. So there's our little piece. It's a little piece of the curve. And so we say, well, we need to figure out what's the radius and what's the length and put it all together. Okay, let's start with length. That's usually the hard part of these computations. Okay, well, so for length, we need our x prime and our y prime. So as a reminder, the first slot is your x. The second slot is your y. Okay, log of secant plus tangent. Do we know the derivative of that? And is there a shortcut? Does anybody know the derivative of log secant plus tangent?
Just secant, right?
Well, let's look at our formula sheet. And we can look in this portion here. That's the portion dealing with derivatives and integrals. And you can ask, does anything look like log secant plus tangent? That looks an awful lot like log secant plus tangent. So it says here, the integral of secant is log secant plus tangent. So the derivative of log secant plus tangent has to be secant. All right. So we get that x prime of t, And you could just do it the long way. There's no problem with that. But why not use short ways if we have them available? What's the derivative of sine? Cosine. And you have to keep track whether you're taking integrals or derivative, because sines and cosines have these weird rules. What's the derivative of just the cosine? So y prime of t. Derivative of cosine? Negative sine. Okay. Well, moment of truth, I guess. All right. So we're going to take x prime squared plus y prime squared. Secant of t minus cosine t squared plus negative sine squared. And at this point, you might get nervous. Like, uh-oh, is this going to be nice? Is this going to be something we can integrate? But you should have faith. And you should have faith that when we ask you to find an answer, that it's findable. If we ask you to set it up, hopeless. But here, they ask you to find it. So good things should happen. If we've lived a good, clean trigonometry life, nice things will happen. So let's square. So we have our a squared, secant squared. And at the end, we'll have a b squared, which is cosine squared. And then we'll have a term in the middle. What goes in the middle? So we have your a squared, you have your b squared. This is a minus b squared. That's what I'm talking about, a squared, b squared. What goes in the middle? 2ab, right? And it's going to be a minus 2 secant t cosine t. Sorry, it's a little squish there. And then, of course, we'll also square the sine squared. Now, cosine squared plus sine squared, that has a name. What do we call that? Yes, it is the 1. Secant times cosine has a name. What do we call secant times cosine? Also 1. Because secant is 1 over cosine. So what do we have? We have secant squared minus 2 plus 1. So this becomes secant squared minus 1. But secant squared minus 1 has a name. What else can we call secant squared minus 1? Tangent squared. Because there's an identity. It's on the formula sheet. Tangent squared plus 1 is secant squared. So that's like, whoa, x prime squared plus y prime squared. There's a name for this. Nice. Now, why do I say nice? Because it's a square. We want x prime squared plus y prime squared to be a square, because we're going to have to take a square root. All right, so here we go. Our length is the square root of tangent squared, t dt, which becomes tangent of t dt. All right, so there's our length computation on the side. Now we're ready to do the rest of the work, which is the radius and, of course, the bounds. Well, for the bounds, that won't be too bad. Where do we get a and b from? Do we figure out where these x values are? Do we figure out where these y values are? Or do we do neither? What will a and b be? We use the t values. All right. So we're going to go from 0 to pi over 4. Now, our radius. That's how far away that little piece of the curve is from where we're spinning. So here's our radius. What does that correspond to? Okay, you said cosine t, but in general, just looking at the picture, y. Start with like a simple explanation. It's y. And then you build up. Well, y is cosine t. So we have our 2 pi. I keep forgetting to put these 2 pi's in. Our radius is cosine of t. So this is our radius. And our length we did over here is tangent of t dt. Now, what is another way to think of tangent?
Sine over cosine?
Tangent, sine over cosine. So if you take cosine times tangent, what comes out? Yes, we saw the sign, and it opened up our eyes. We saw the sign. Do, 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 do. This fills us with hope. This feels like something we should be able to integrate. What's the integral of sine? And be careful. Negative cosine. So we have minus 2 pi cosine t. Evaluate from 0 to pi over 4. Well, the good news is that should we need it, let me point out some things. Tangent being sine over cosine is on the formula sheet. Secant being 1 over cosine is on the formula sheet. Tangent squared plus 1 being secant squared is on the formula sheet. And then we have our nice table of values is on the formula sheet. So if you plug it in, cosine of pi over 4, root 2 over 2, cosine of 0 is 1. And, well, you can distribute the minus through. So we end up with, let's go ahead and distribute the 2 through as well. This becomes pi times 2 minus root 2. Once you clean it up. All right, good. Whew. It looked a little bit scary initially, but then it worked itself out. Beautiful, beautiful. All right, any questions on that one? Okay, good. In that case, let's do one more application with length. And so mass in a one-dimensional setting, we've talked about mass of like a rod, which you can imagine is on the axis, the x-axis. But we could have mass of a wire. So we have a bent wire. We could say, well, how much mass is there? So we need to understand what is the shape of the wire, and that's given by a curve, parametric curve x and y. And then we have the density of the wire, which is given by a density function. So, all right, well, our generic formula says that mass is the integral, adding things up. Density times measure is what the formula sheet says, but for one dimension, what we call measure is another name for length. So we say, all right, so it's really density times this length. And so we say, all right, well, we have all our pieces, and we just go for it. So what should we start with? What should we do first? Length is pretty good, because whenever you have a length term involved, that's going to be where you have to put a lot of your effort, because dealing with square roots can be challenging. So it's good to get that out of the way. Okay, so let's make some notes here. So here we have x of t is t squared plus t over root 2. So x prime of t would be the derivatives, 2t plus 1 over root 2. And y prime of t, similar, will be derivative 2t minus 1 over root 2. So we have our x prime and our y prime. Okay, so now we plug in our formula for length. So that's our square root x prime of t squared plus our y prime of t squared dt. Well, sometimes we should have just probably computed x prime plus y prime squared first, but let's see where this gets us. I haven't done this one. I hope it works out nicely. I think this is from a recent final, or maybe a recent exam. I think last semester maybe. 2t plus 1 over root 2 squared plus 2t minus 1 over root 2 squared. All right. Well, what do we do? Not a lot of options. Probably we have to square stuff. All right. So this will become 4t squared plus, and then we'll have 2t times 1 over root 2 times 2. So plus 2 times 2t times 1 over root 2, whatever that turns out to be, plus 1 over root 2 squared is a half. And, okay, I ran out of space, plus, we'll keep going on the next line, 4t squared minus, because there's a minus sign, 2ab, and then plus a half. That's all there, dt on the outside. Well, does anything happen? Okay, if nothing happens.
Cancel out the middle values.
Well, we can cancel out these values. Whoa. Okay. Well, that becomes the square root of 4t squared plus 4t squared makes 8t squared, and half plus a half makes 1. All right. Now, bad news. That's not a perfect square on the inside. So that's going to make things a little bit more challenging, usually. But we're not just integrating length. So if we were going to integrate length, we'd be like, ugh, ugh. Now, we may not make those noises out loud during the exam, but we'd feel those noises. But remember, that's just a piece. Okay, so let's put it together. What's our density? That's also coming into play, right? So our mass, we have our A and B, integral 0 to 1. Density, 8t. And then we have length. And instead of square root, I'll write this as 8t squared plus 1 to the half. And dt. So here's our length. Can we integrate this? And how do we do it? Use substitution? Excellent choice. It's almost your go-to, right? If you can't integrate it right away, then you say, well, can I do some simple algebra? No. Can I do some trig identities? Definitely no trig. And you say, well, let me think of substitution. Is there a nice substitution in play here? Well, we don't want to substitute here. This is sort of on the outside. Think about substitution. Substitution, you should be looking for something on the inside. Is there some expression that's on the inside of a function? Yeah, this is on the inside. Substitution is an inside job. So let's think about that substitution. Now, it may or may not be a good substitution, but it doesn't hurt to try. So we take the derivative, 16t dt. And we're like, oh, so close. Because we have a dt on the end, we have a t, but we have 8 and not 16. Oh. But wait a second. These are numbers. We have a lot of flexibility with numbers. So we could say 1/2 du is 8t dt. And now we're like, oh, nice. So updating, this will become the 8t dt will have a half, and half is a constant, so I'll put it out in front, du. This 8t squared plus 1 is u, so a u to the 1/2. Anything else we need to do? The bounds. Don't forget the bounds. Now, we were in bounds for t. These were our t bounds. They went from 0 to 1. We need to go to u bounds. So, when t is 0, what does u equal? 1. When t is 1, what does u equal? 9. 8 plus 1. And we're like, ooh, 9 is nice because there's a square root. And it turns out square root of 9 is a reasonable number. Okay, so we get 1/2. What's the integral of u to the 1/2? So add 1 to the exponent, 3/2 power, multiply by the reciprocal, 2 over 3. And we're going to do some evaluating. And the nice thing here is that the 1s, sorry, not the 1s, the 2s cancel. Okay, well that gets us to 1/3. And now we have to deal with 9 to the 3/2. And we say, well, of course, 9 cubed is 729. And the square root of 729 is, altogether, 27. Good, good. You got this, right? Now, you might say, no, that's not how you do that, Steve. Oh, you're right, you're right. Do the thing that makes it small first. Square root of 9. 3. 3 cubed. 27. So 27. And then 1 to the 3/2, well, 1 to any power is 1. And 27 subtract 1 gets us to 26 over 3. And there we go. All right. And as I said, this was from a recent exam, so if you can do this, good. If you weren't able to do it yet, that's okay. You still have time. But start getting ready. Who knows what lies ahead? Who knows what evil lurks in the hearts of men? All right, any questions? Good. So, those were examples involving length. Let's talk about area. Now, area does not involve length in the formula. It's not on the formula sheet, but we know how to integrate area. So here we have a curve called the cycloid. And we have it in parametric form. We have our x of t, t minus sine t, y of t, 1 minus cosine t, and t goes from 0 to 2 pi. Now, if you look at this and say, this curve looks familiar. Well, you can actually trace it out in the following way. Imagine, if you will, you had a bicycle. And so now you'll see I don't know how to draw a bicycle. But okay, so imagine I could draw a bicycle. All right, here's a person riding their bike. Do the following. Put a little dot right there on the front wheel, and then start rolling the bike forward. And just trace where that dot goes. The answer is it makes this shape. So this is where it comes from. And there's lots of fun stories about this shape. But for now, we want the area. Now, back in the day, back in our day, we would have said, well, if we want the area, we'd split it up into rectangles. That was our thinking when we had a function y equals f of x. Here's what we're going to do. Actually, let me ask, what do you think we should do now? For parametric, what should we do?
It looks like a semicircle, so I'm thinking like something you might do with a circle.
Oh, but it's not a semicircle. That's the hard thing. The answer, we're going to chop it up into rectangles. The idea is so nice, let's just reuse it. We're not going to go reinvent the wheel. We just may have to think about it. Okay, so we're chopping things up into rectangles. All right, so now channel your inner Calc 1 student. And for many of you, that wasn't so long ago. I want to integrate. I'm thinking of chopping up into rectangles. And this might be the first guess. I say, well, great, Steve. I like rectangles. You like rectangles. We all get along. We'll go 0 to 2 pi, and we'll do our height. Right? Because that's how you find the area, right? The height. You integrate the height. Is that going to give us the right answer? And why not? Okay, so it won't give you the right answer. What's wrong with this guess? Sorry, what? So think about what's going on here. What is y a measurement of? It's a height, right? Good. What is t a measurement of? Time. Does height times time give you area? No. Height times time does not give you area. So the little slices are not measuring the right thing. So we say, oh, well, this is wrong because we don't have height times width. So you see, when you talked about integration before, you had your integral of f of x dx. That dx meant something. It meant your width, that change in x. And now you're like, oh, idea, a better guess. So, we'll still measure things in terms of time. We like our height, good for us. What is the width? Well, it's like a small change in x. How do you find a small change in x in terms of t?
dt?
Well, dt won't be a change in x, it'll be a change in time. So how do we get x, a small change in x involved?
dx over dt?
Sorry, what?
dx over dt?
Well, it's kind of like dx over dt. We are going to, let's talk about this first. X prime of t, change in x. Now, is this correct? And why not? Well, it's not quite the same. This is still a height. What is x prime of t? X prime of t is actually not a width. What is it? It's the rate your width is changing. So how do you go from a rate your width is changing to a width? So let's think of it another way. Let's phrase it in terms you're more familiar with. How do you go from speed to distance? Speed times what gives you distance? Time. So x prime of t dt, x prime of t is how fast x is changing, dt is how much you've changed in your t. So x prime of dt, that's your width. So here's your height, and here's your width. All right. And this will work. This is correct. This will find the area. All right, so for us, we'll have the area is equal to integral 0 to 2 pi, height, 1 minus cosine t, and times width. What's the derivative of t minus sine t? 1 minus cosine t. Now, we could work this out, or I could make some other comments. What do you want to hear? Or if you want, I can work this out quickly.
Speed run, go.
Speed run. Whoa. It's 17. No, it's not. But if you multiply this out, this becomes 1 minus 2 cosine t plus cosine squared t. And our initial reactions are 1, we like that. Cosine t, we like that. Cosine squared, not so much. We don't have a nice way to do cosine squared. Or do we? Turns out we do. Which is to say, we're not going to integrate cosine squared. We're going to replace it by something it's equivalent to. So cosine squared, there's something called power reduction. So cosine squared is a half times 1 plus cosine 2 theta. And we're going to do a lot of this in the next phase of the course, and we're going to do a sum of it in the near future. So we say, okay, so this is really 1/2 plus 1/2 cosine 2t, and now we're happy. Okay, so updating 0 to 2 pi, we'll have 3/2, which is 1 plus 1/2 minus 2 cosine t plus 1/2 cosine 2t. Well, that's 3/2 t minus 2 sine t plus 1/4 sine of 2t. And we go from 0 to 2 pi. Well, when you plug in 2 pi, actually, let's plug in 0 first. 0, that's 0. Sine of 0? 0. Sine of 0, 0. 2 pi. Sine of 4 pi? 0. Sine of 2 pi? 0. So we end up with 3/2 times 2 pi, which is 3 pi. And that's the answer for the area. Okay, so that's if we did vertical. Could we do horizontal? And why weren't you stressed about orientation? Well, let me talk about where orientation came into play. Do you see this arrow here? It's going in this direction. What happens with the sign of x prime of t dt? If we're moving this way, what's the sign of x prime of t? It's positive. So sign is positive. Now, what if we had been going in the opposite direction? Would we have gone 3 pi? No. We would have gone negative 3 pi. We'd have to have a correction here because the sign would have been negative, so you have to correct. So essentially, orientation, you might have to add a plus or minus. That's what it boils down to. Orientation comes down to a plus or minus. Now, there's 2 fun things we can do. One is we can break up into horizontal, or the second thing we could talk about volumes. Which one do you want to try? Oh, horizontal is fun. Okay. Now, instead of integrating height times width, could we integrate width times height? So, let's think about what that would be. Integral 0 to 2 pi, width times height. Well, what part measures your width? X measures your width. What part measures your height? The y. And so what we're going to do is we're going to call our change in y prime of t dt. Will this give you the right answer as it's written?
Yeah.
The answer is no. It will not give you the right answer. But you can fix it with one line. This will give you the right answer for this picture. Now, there's an orientation issue. That's why you needed the minus. Now, not every time will you need to add that minus in. And don't think of like, oh, it's the y prime, x prime, and minus x, y prime. It depends on the situation. But I claim this will work. And it doesn't feel like it should, which is why it's really cool that it does. So let's talk about what's going on. When you're over here, let's suppose I'm here on the curve. What's my rectangle look like? Well, it looks like this. And now you're saying, whoa, that's not right. That's definitely not what I want to be counting. That's true. You don't want to be counting that. Now, what happens if I'm over on this side? What does my rectangle look like? Well, it'll look like this. It'll go the whole length, back and forth. But again, it's not quite what I want to count. But now, here's the fun part. Think about the signs. What's true about y prime of t on this stretch? It's going down. Y is going down, so y prime t is negative. What's true about y of t on this stretch? We're going up, it's positive. Now, because of that negative, that's how we fix things. So on this stretch, this first little rectangle is a minus rectangle, a negative area. This rectangle is a positive rectangle, positive area. When we put these two together, what happens? Cancellation. So you end up with only this stretch here. So when you start thinking about the rectangles, it seems too good to be true. But when you start thinking about, orientation, you have some parts being added and some parts being subtracted, it works out. So it's really clean. Okay. Well, in the interest of time, we have to move on and talk about our new topic. Okay, so what's our new topic? In the last 5 minutes. Don't worry, the new topic is pretty quick. We're talking about coordinate systems, which are ways to describe the plane. Now, we're not changing the plane. We're not changing what's in the plane. We're not moving the points around. The only thing that's happening is we're describing points in different ways. Now, there's two coordinate systems that you'll see for 2 dimensions. The Cartesian coordinates are the ones you're most familiar with. They're named after René Descartes. The legend goes that one day he was sick. And back in his day, they had not yet invented Xbox. So he didn't have much in the way of entertainment as he laid in bed. So he just sort of stared at the ceiling, and there was a fly on the ceiling. He thought, wow, that's an interesting fly. How could I describe where the fly is? And it occurred to René that, if I see a fly, I can describe it by saying, how much have you moved off of one wall together with how much have you moved off of another wall? So you have a pair of distances. And so when we talk about the Cartesian coordinates, we have these x, y, which are really measuring distances. How much have I moved in 2 directions? The x coordinate tells you how much you move in the x direction. The y coordinate tells you how much you move in the y direction. Now the second system, polar coordinates. So polar coordinates, they say, well, look, don't think of it as I'm a person viewing from afar and I see the whole thing. Suppose I just want to say, how is everything related to where I am? You can imagine you're on a ship in the middle of the ocean. What makes sense to know about things' location relative to you? Well, you say, well, relative to me, I need to know 2 things. Which direction is the object, and how far is the object? Now, if you start thinking about that, you probably are familiar with the idea of radar. Radar works by saying, I have this measurement, this central thing where I can measure where things are relative to me. So what do I need to know? Well, if I have a point, say here's my point, I need to know which direction to face. So I have an angle measurement, which tells me how far I have to pivot. And then I need to know how far out I need to go. So I can imagine that I'm at a central point. I have an understood this is direction 0. And I say, okay, how much do I need to pivot? How far do I need to move forward to get to my location? So now we have a direction and a distance. So the direction is the angle, and the distance is r. So r and theta. And as I said, these both describe the plane. So what you can do is you can stack them right on top of each other and say, well, how can I describe a single point? Well, I can describe it in 2 ways. I can say, well, I move x in the x direction, I move y in the y direction, or I pivot an angle theta and go a distance r. when you put it together, a very nice friendly shape emerges. The triangle. And we like triangles. And so we get a couple of facts very quickly. Pythagorean theorem, x squared plus y squared equals r squared. Right triangles, x equals r cosine theta, and y equals r sine theta. Now, one last note as we finish up for today. In Cartesian coordinates, every point has a unique pair. And you give me a pair, that's uniquely determines the point. Now, it is true, if you give me an r and theta, there's a unique point I'll get to. But in polar coordinates, it is the case that I can describe a point in multiple ways. So be careful. One thing that can happen is that I can spin around and get dizzy. I can add multiple revolutions before I move out. I might stagger a bit, but keep in mind that I can add multiples of 2 pi. And the other thing that can happen is if I add a multiple of pi, I'll be facing the wrong direction, but then I can walk backwards. Negative r.